So, final application for derivatives is what are known as related rates. And these are equations that involve two or more variables that are all differentiable with respect to time. And that's really important, is that when we're talking about these, we're doing derivatives with respect to time. So this goes back to the implicit differentiation. If you're taking the derivative of any variable that's not t or whatever stands for time, you have to do the chain rule on that variable. So for example, if we look at perimeter of a rectangle, we say that the width and length are changing, and we want to see how, the rate at which the perimeter changes as the width and length do. We start with an equation for perimeter, and then we do our implicit differentiation with respect to time. So derivative of p would be 1, but that's not time, so I need dp dt, derivative p with respect to time. Derivative of 2w is 2, but then chain rule on the w, since I'm doing this with respect to time. And 2 times L derivative is 2, but then I need derivative of L with respect to time. And this is our related rates equation here that we're going to then plug values into to find dp dt. So in terms of a strategy to solve these, it's very similar to when you're doing optimization. I will say pictures are a gigantic help with this. Remember, your picture doesn't have to be good on the AP exam. It's not an art test. This is a picture that is meant to organize information for you because there's a lot happening in these problems. Lots of things moving and changing, whereas other things stay the same. When you draw your picture, the only numbers that go on the picture are the constants, things that aren't changing. If there's something that's changing, put a variable there. And then off to the side, make a list of the values of those variables at the moment in time you're being asked about. And then it helps to actually write down what are you trying to find, because you are going to see there's lots of information in these. Once you do, you just need to write an equation. And in some ways, this is easier, in some ways tougher than optimization. With optimization, whatever you were finding a max or min of is what you wrote an equation of. Here, with related rates, you can write any equation you want as long as it involves the variables that you're talking about. Once you have it, you take the derivative with respect to time, plug in the values you know, and solve it for the rate that you're looking for. And again, make sure you're tying your answer back in to the original problem statement. So here, if we look at the case of a hot air balloon that's rising straight from a level field, so level field, hot air balloon. So you can see why it is that we have a rangefinder on the ground that's looking up at the balloon. Now, as it's rising, the height of the balloon is changing, so I'm just going to put an H because that's not a constant. The rangefinder is 500 feet from the liftoff spot. That's not changing, so I'll put the 500 there. We're being asked, and then we're told that the elevation angle at the rangefinder is pi/4, but that's changing, so I'm going to put a theta here. So I'm told at some moment that theta is pi/4 radians. The angle is increasing, so that would be d theta dt, the rates that theta is changing. Is increasing means that we have a positive rate of 0.14 radians per minute. And we want to find dh dt. So that means I need to find some equation involving the h, the theta. The 500 might get used or not, but I notice I do have a right triangle, and I know I'm dealing with opposite and adjacent sides. So I'm going to use the tangent of theta is equal to h over 500. So taking the derivative with respect to time, I'd have secant squared theta times d theta dt equals 1 over 500 times dh dt. I know the d theta dt. I'm looking for dh dt. I need secant squared of theta, but I know theta is pi/4. Secant squared is 1 over cosine squared. Cosine of pi/4 is 1 over rad 2. Reciprocal of that is rad2 squared is 2. So this is going to be 2 times 0.14 equals 1 over 500 dH dt. Multiply each side by 500, and I get that dH dt is 140, and then h is being measured in feet because our distances are measured in feet. Time is being measured in minutes. And there we have our solution.